Welcome to this second last session of the day. This is the myth of the magical messaging fabric. My name is Jakub Korab. I am an independent consultant. I specialize in systems integration and messaging. In particular, two pieces of software that I'm going to talk to you about, and we'll talk about the myths around messaging and where they come from and why they might be useful and that sort of thing. I've been doing messaging for a very long time, and every single time that I visit a new client, it becomes apparent that they kind of don't really have the full picture of what's going on. So today, I'm going to help you get more of the picture and help you to reason about these things and shed a bit of light on this slightly mystical area. But first, I'm going to talk about myths. What exactly is a myth? Well, this is one definition. It's an idea or a story that's believed by many people, but that is not true. Now, I think that's a very simple explanation and a little bit unfair, because it's quite dismissive of what a myth is and the purpose that these things serve. So I prefer this one. It's a usually traditional story of semi-historical events that unfolds part of the world view of a people, or explains a practice, belief, or a natural phenomenon. So myths are stories about our world that are partially informed by our experience, partially through that of others, and they help to guide us. And it's the usefulness of that guidance that explains why we as humans tell myths, because they have a grain of truth to them and they fill in a gap in our knowledge. So what's mythology? Well, mythology kind of comes from two Greek words, mythos and logos. Logos is the root word of logic. Logical thinking kind of approaches the world scientifically and empirically. So with logical thinking, you look for explanations and guided by things such as facts. You're guided by experiments and deduction. So truth that's discovered by logos seeks to be objective and universal. And how do you get more logos? Well, you get it through time and some experiments and reading the documentation. Who here reads the documentation? I thought so. So this is where mythos comes into it. And mythos approaches the world through a less direct and more intuitive means. So with only a partial grasp on objective truth, we kind of fill in the gaps of our worldview with mythos. So like the blind man feeling an elephant, we feel the elephant's leg and go, well, what's the elephant like? Well, the elephant's like a tree. I can put my arms around it. Yeah, if you touch its tail, well, an elephant's a bit like a snake. Yeah, it's long and it's got this weird thing there. So in IT, we're not immune to this. So we get these half-truths through answers on Stack Overflow to the wrong questions. We get it through half-read technical articles, and we get it from glossy conference presentations by vendors. So let's talk about messaging, because this is the root cause of why we're here. What is messaging? Well, it's the movement of data between systems through the use of an intermediary, and I'm going to limit it to that definition. Okay? We're going to use something in the middle. Messaging is not glamorous. It's half-jokingly referred to as plumbing and dismissed. And that's a shame, because plumbing is integral to so much of what it is that we do. We all have limited time and attention. And in an industry that's as fashion-driven as ours is, where everything superficially seems to be moving so quickly, people often tend to focus on the shiny technologies. Does that just sound about right? Yeah. So partially because they're cool, and partially so that we don't get left behind. And the things that are the most ordinary don't necessarily get the attention that they deserve. And so we forget they're there while we're busy with other things. The people who looked in detail at these things and who understood them move on, they go elsewhere. And we're left with gaps in our knowledge and half-remembered stories about what to expect from these systems. So we fill the gaps with myths. So what is the mythology of messaging? It's not uncommon to hear things such as, we will never lose messages. Messages will be processed in order. Of course they will be, right? Adding consumers will make the system go faster. True? Messages will be delivered once and only once. And we should just be able to add this extra million messages a day. Just is a very, very dangerous word. And all of these myths start from one root myth. It's just a pipe. Just a pipe. And this is where the hand waving usually starts. But if you look closely, you'll see that there's a lot of things going on here. So by telling these stories, we transform something that's everyday and functional into a thing with wondrous properties. Inevitably, later on, usually in production, we are disappointed with the results. So to get past this state, we need to get a deeper understanding of what it is that we're working with. So whether a messaging platform can address your use cases and how it goes about it depends on its underlying design and the trade-offs that its authors chose to make. Sometimes they're obvious. Other times you need to get a deeper understanding of what's going on. And this means drilling beyond the front page of the documentation and a few conference presentations. So I'm going to talk to you about messaging through the lens of two products that superficially play in the same space, the distribution of messages. Okay? They have deep differences in approach and use cases that they target. And my goal here isn't to explain these things to you in detail. Rather, it's to highlight through their differences ideas that you need to think about in order to sensibly critique those systems in the future. So let's talk about why we'd use a broker-based messaging system at all. If we've got two separate systems, A and B, they have to agree on a contract to interchange messages. Okay? So now we have one system talking to another system. Why would we stick in something into the middle? Well, it's to give a separation of the two systems beyond an interface, because it gives it a separation over time. A consumer doesn't need to be there when a message is sent by a producer. It's similar to a post office system. When you send a parcel, when you go to the post office, the recipient doesn't have to be at home. It automatically kind of ends up appearing. And we simply just trust that the package will be delivered at some point in time. So let's take a look at ActiveMQ. What are some of the goals? Well, it's a free open source JMS implementation. JMS is a messaging standard that seeks to provide a kind of a standardized interface over two kind of messaging domains. I'll get to those in a second. It's a general purpose messaging broker. General purpose is the key here. It's not specialized for anything. You can kind of use it for a lot of stuff, right? And it allows clients to interact with it via multiple protocols. So let's see what a broker like this looks like. Well, there's actually two parts of this thing. A broker is actually one part of a messaging system together, which is known colloquially as a provider. A broker is the server side. Then you've got a client where you've got your code talking through an API to some sort of a client library that deals with the actual communication with the broker. Okay? So a messaging system has to be understood in the context of both of these things. You can't say definitively whether a messaging setup is correct by only looking at one side. Both parts work together. The client-broker communications are performed through the use of a wire format. So what exactly is this? Well, in this system, when you look at messaging, messaging is a lot like a sausage. Yeah. Don't ask too much about what's inside as long as it tastes good. So a wire format is the thing that allows the broker to communicate with a client, and likewise. So ActiveMQ supports OpenWire, which is an internal wire format. It supports AMQP 1.0, which is a language agnostic format. It means that you can use a client that is AMQP compatible from any language that supports a client. In C, C++, Python, all those things, these things can talk to ActiveMQ through something called the Cupid Proton client, for example. There's STOMP, which is a text-based protocol, MQTT, which is an IoT protocol for publish subscribe, XMPP it's kind of like a chat room-based protocol, and also WebSockets. So you can have a JavaScript client talking directly to a message broker without a web server or anything in between. So ActiveMQ supports two messaging domains. The first one is point-to-point, queues. This is a first-in, first-out data structure that is durable. What exactly does durable mean? Well, durability is a quality of service measure. And what it says is that if the receiver goes away, then any messages that have been received by the thing in the middle will be able to be picked up by it when the consumer reconnects again. Okay? Messages can be persisted by the queue or by the broker if the sender wishes them to be. Okay? Durability and persistence are often confused, but they're two very different things. Persistence is simply about keeping the messages around if the broker itself shuts down. When it comes back up, if the messages were persisted, it can just keep going from where it left off. Okay? Durability doesn't equal persistence. So this is the domain that we're going to focus on, primarily because this is the one that we're most often interested in. 90% of use cases have to do with queues. ActiveMQ also supports topics, publish, subscribe. Topics are non-durable, so these are more like a conference call. If you're on a conference call, you hear everything that's been said. When you hang up the phone, you miss the conversation. When you connect again, the conversation is continuing without you've missed anything in the middle. They can be made durable, so the consumer going away receives the messages later. And they can also be, durable conversations can also be persisted. Okay? So now that we've got some basic definitions, let's consider a trade-off that every single network-based system has to make, that accepts data has to make. It's what I call the reliability versus performance trade-off. And you have a spectrum on single-node systems. Okay? You've got reliability on one hand and performance on the other. This is tunable. JMS, which is what ActiveMQ supports, sets the default pointer on this all the way to reliability at a cost of performance. However, you can set it to anything you like, until you get just the right sort of mix in performance to reliability that you're comfortable with. So to understand brokers and how they actually go about storing messages and how it affects this particular trade-off, you need to understand how these things actually get persisted, where it gets stored. And that's where a journal comes in. A journal is a persisted data structure. It contains a history of interactions with the broker, stored across multiple files. In ActiveMQ, it stores messages that are incoming and also acknowledgements. Okay? So that when a broker gets turned on, it looks at its journal and goes, oh, I'm in this state. And it keeps going. Okay? So let's take a look how messages actually get sent in and how they interact with this journal. This is a necessarily simplified model, but it's a decent enough kind of working model just to get you to think about it. So you've got a sending thread that's kind of coming along here inside a producer. And at some point in time, you say to your messaging APIs, I'd like to send a message to a queue. So producer will send a message over to ActiveMQ, and ActiveMQ will write it into the journal, usually on disk here. Okay. It then needs a confirmation from this disk. Now this confirmation is the slowest component of the entire interaction. Okay. I'll get onto it in a second. Once ActiveMQ gets that confirmation, it sends an acknowledgement back to the producer, and the producer continues. So while all of this stuff is going on, this thread is not doing anything. Okay? So why exactly is a confirmation necessary? I've written something to disk. Why do I need to actually confirm it? Well, a disk isn't exactly what you think it is. When we write to a disk, we actually have a number of buffers between our program, in this case ActiveMQ, and an actual physical medium. whether that's RAM or whether that's a spinning magnetic platter. So the first one is the operating system buffer cache. And this caches frequently read blocks, and it combines disk writes into each other so it's not hitting the disk all the time. Okay? Every once in a while, this might get flushed otherwise. Okay? At which point in time, you would hit a disk drive controller cache. Especially in RAID systems, you find these things so that you're not trying to hit multiple disks at the same time. Okay? Some of these are write through. Others are write back, which means they accumulate data and periodically dump. Usually they're volatile, which means that if you turn the power switch off, what's going to happen with that data? Pfft, gone. So let's say that we've gotten past the disk drive controller cache. We hit a disk drive cache. Again, this might be write through or write back. On consumer drives and SSDs, which are actually used in servers a lot of the time, these things are write back, so again, buffer up and then periodically write back, and they're volatile. Again, if you turn the power switch off, gone. So in order to actually get past all of these things, you need to send a signal. Yeah? And most of these signals for buffer interaction are only available to the file system. From Java, there's an operation called sync, and it forces all the system buffers to synchronize with the underlying device. This is massively slow. 3 orders of magnitude, usually, slower than a single write. Why? Well, because a single write, we've only actually hit the operating system buffer cache. Yeah? So we've got to go through all of these buffers in order to actually get something to go to disk. Okay? So in ActiveMQ, the disk is the main speed limiter, but it's not the only one. So let's talk about disk performance factors. Okay? So when we're writing to a disk, it's useful to have a mental model as to what's going on. So I'm going to use this mental model of a pipe. Okay? You're at the top, you're saying, I'd like to write some stuff to disk. How fast can you write stuff to disk? Well, it depends, because there's a number of dimensions to this pipe. The first one is instructions per second, what's called IOPS. This is kind of a weasel word used by vendors, because it means something different depending on how you're operating with the disk. Are you doing writes? Are you doing reads? Are they random? Are they sequential? Are they mixed? In what proportion? All of these will give you different numbers. If you ever try to do this and try to work out what IOPS actually mean on Amazon, good luck to you. So the next one is the length of the pipe. And the length of the pipe more or less corresponds to the latency. The longer the pipe, the longer it takes. Okay. The width of the pipe, on the other hand, is the carrying capacity of the pipe. So how large can each of those individual instructions be in order for me to get the maximum throughput that I can out of this particular disk? Okay? So the overall throughput will be defined by the first of these limits to be hit. Okay? So as I said, disk performance is the main limiting factor of ActiveMQ performance, but it's not the only one. Well, because you've got internal contention as well. So if I've got 3 producers all wanting to write to different queues, well, they've got to write to the same journal. So somewhere in the middle, they actually need to synchronize. Yeah? Parallelism or concurrency is about preventing parallelism. Okay? So here, we're using some form of mutual exclusion, or simply just synchronizing. Okay? So why is this necessary? Well, if you've got 3 different things trying to write to a file at the same time, they'll overwrite each other's stuff. Right? So we obviously don't want that. The beauty of this little design choice to have some sort of synchronization is that if you put all of the messages in one journal, it makes it really, really simple to do transactions. Okay? So let's say how transacted sends would work. Well, if I want to send to a number of messages, do I need to get confirmation every single time? No, not really, because the transaction says all or nothing. Yeah? So the client library can make some optimizations. It can say, hey, send to QA, send to QB, send to QC, and then finally commit. And only on that commit will we do a write, a confirm, and an ACK. So what we've done in that transaction, if you think about the 3 dimensions of a disk write in that pipe model, we've done one write. And we've just used up a whole bunch of space in that item in order to do that once. So we get a massive performance increase of that. So we get some additional benefits because the client sends themselves a async. The client doesn't need to know whether the broker received it. Not until the end. Did you get this? Not. Yes, I did. Awesome. Great. Carry on. So this has some nice side effects that it's able to actually tie into broader transaction management APIs, which is pretty cool. So ActiveMQ kind of has 2 halves of the brain. This is about being receiving messages. Now let's talk about distributing them out. If I have a consumer that connects and says, hey, I'd like to get some messages from a queue, it expresses demand. ActiveMQ at this point in time pages a whole bunch of messages into memory and dispatches them over to the consumer. Okay? The messages end up in a buffer here on the client called a prefetch buffer. And they are consumed out of this prefetch buffer. The messages at some point will get acknowledged back to the broker, and the broker will delete them out of the store. So the broker is actually holding on to messages while they're being processed if it hasn't received an acknowledgement. Okay? Now, I've deliberately called this step X and not step 3. Why? Well, because this is tunable. Okay? It's client specific. Your code actually says what it wants to do. A transactional setup is often a good choice in that the consumption of this needs to happen before the acknowledgement actually does. Okay? So when we mark something for delete, we're not actually deleting it out of the journal. We're simply saying, hey, I'm just going to increment a pointer in an index to say that that particular message has been consumed. And any journals which have had all of the messages within them consumed are now eligible for garbage collection at some point. Okay? They get deleted by a background process, and they're periodically deleted. So what happens if you've got multiple consumers on a queue? Well, a producer is sending messages in. Half of them get delivered to consumer 1, and half of them get sent to consumer 2. Round robin dispatch. Very important to understand, okay? Because not all messaging systems work like this. What happens if we get one of these systems failing? Okay, we've dispatched some messages over to it, and then the system crashes. Well, those messages will just be redispatched over to a second consumer. Okay, this is a very simple consumption model, in that the client only has to care about subscribing to a queue in order to receive the messages for it. Okay, and it's the broker's responsibility to keep track of the consumption and ensuring delivery. Okay. What's interesting here is about the timing of the failure. Okay. And it all depends on what the consumer actually does. So if you're talking to some sort of a web service, for example, you may have pulled a message out of the prefetch buffer and called a web service, and then your node has crashed. So you've affected downstream state somewhere else. Now, ActiveMQ never received a confirmation, so it'll just redispatch that message away. Since the broker has no insight into what stage of processing the message was at when the node failed, the message itself may be processed twice. Which leads us to a conclusion. There's no such thing as once and only once message delivery. You can have at least once message delivery, which is what queues give you, or at most once message delivery, which is what non-durable mechanisms such as topics will provide. Okay? This has fundamental implications about how we actually need to think about our message processing logic. So what happens how do we get reliability onto something like ActiveMQ? Well, there's 2 parts to it. The first one is the client. The client is told, hey, I'd like you to treat 2 physical nodes as one logical instance. Okay, so I've got 2 hosts, host A and host B. Okay, and I'll alternate my connection between them until I can connect to one of them. Okay? If I have 2 brokers, they share some storage. That's the general primary mechanism for supporting master-slave in this. Okay, and they use the store as also a locking mechanism. So the first node that starts up will connect to the store and it will get an exclusive lock. And it is then able to open its ports, at which point in time clients can connect to it and start sending or receiving messages. Okay. The broker that came in second starts up, connects to the store, goes, oh, someone else has got the lock. Okay, well, I'm just going to stand back for a couple of seconds, and then I'll try it again. Am I able to become master? No, I'm not able to become master. Am I able to become master? No, not able to become master. Am I? And so on and so on. So what happens if a node crashes? Well, the node that's been checking is now able to get a lock because it's been released. It opens its ports, and the client is now able to fail over. Okay. So with this particular type of setup, disk access matters, and the disk location matters, and how it's accessed matters. If we have ActiveMQ, not only do two physical devices need to be connected in such a way, wired up so that they're hitting the same store, but they should also be set up in such a way that no processes come in the side and access the same disks. Why? Well, if all of a sudden someone starts using disk heavily, the broker's going to slow down for no apparent reason. This is a massive problem, especially in highly virtualized environments, because you have no idea where the disks are, and you have no idea what's using them. You only know that the broker has gotten slow. Yeah? So you need to guarantee a clear run to the disk. For this reason, about the fact that the disks need to be set up in such a particular way, systems like ActiveMQ aren't a good fit for containers. Why? Because they need a manual box setup in order to be set up. So by containers, I'm talking things like Docker. There are systems like Flocker that allow you to have some sort of storage that moves along with a container. They may or may not work particularly well for these particular requirements. You should also be really, really careful if you're running your brokers in some form of orchestrated environment, such as Kubernetes. Brokers can't just run anywhere. They need to be running on a piece of physical hardware that gives them a pipe running down to a disk in such a way that that pipe cannot be interfered with any side processes. Okay. If you want to get more of a feel about this, there's a presentation by some people from Salesforce about how they containerized all of their stuff except their databases and their message brokers. Why? Because you need physical access to the disk and you need to guarantee a clear pipe. There are only so many ways which you can kind of virtualize away the hardware. Okay. So how do you scale this system up and out? Well, the first one is you increase the disk speed. Faster disks, faster performance. You can make better use of the disk dimensions. Okay, so if you're doing things like transactions, you're getting wider writes rather than more writes. Okay. Alternatively, you can split the messaging over multiple brokers, and you say, okay, these queues are going over here because they're really, really high volume, and all this weird batch stuff that I've got going on at 2 o'clock in the afternoon, well, we'll just put that over a dedicated broker so that these two things don't interfere with each other. Okay. The biggest problem that I see when I go out on site is what I call the big bag of messaging. We take a whole bunch of systems together, A, B, C, and D, and you say, well, everything can talk to everything. Do not, under any circumstances, do this. Okay? If you replace the ActiveMQ block with Oracle, would that be the same Oracle database? Probably not. Okay? ActiveMQ has to be thought of as a messaging layer rather than kind of one single instance to fix all of your messaging problems. Okay, so some thought is required. So there are some trade-offs to be had here. It's a very simple model, maybe a little bit too simple. You can download it and you can run it. Awesome. in production. Yay! And it works until it doesn't, about 6 months later. It's transactional, which is pretty neat. And it has a rich set of supporting functionality. So you've got things like message routing, wiretapping, broker networks for wide geographical distribution. So there are trade-offs as well to be had. Performance is pinned to the disks, obviously. And performance is impacted by the total load on the broker. It's not about the disk. You've also got to deal with the concurrency going on around the exclusivity mechanism. And it requires transparent changes, non-transparent changes to the broker topology over time. So which systems use which brokers? Why? What triggers these changes? Well, you might have different traffic volumes over time. You may have different numbers of destinations. More messaging gets put on because this other team over here goes, hey, that stuff that those guys are doing is really, really awesome. And it is, until they also put their stuff over the same brokers, which becomes problematic. And it requires an understanding of the internal mechanics and some upfront thought to get right. So let's talk about Kafka as a counterpoint. In order to understand where Kafka is coming from, you have to understand its backstory and its reason for being. So Kafka was designed at LinkedIn in order to get around some of the problems of multiple separate data feeds being fed to multiple systems. Okay? It's intended to address some of the shortcomings in ActiveMQ, namely this idea that you have to set up different brokers for different purposes. You go, well, wouldn't it be great if we just had this fabric that we could throw messages into and not worry too much about it? Okay. So its primary use cases were really around things like moving logs, giving you notifications of UI activities, and monitoring various types of events. They're quite different to some of the more traditional messaging use cases that we may have encountered, such as placing an order in a bank for a €1 million transaction. The value of that message is quite different to the value of moving a log record. Yeah? So what are Kafka's primary goals? Well, firstly, be fast. Really, really, really fast. Kafka is super fast. Kafka is faster than a disk. How's that possible? Get to that in a second. Well, it's supposed to handle huge volumes of data. How huge? Well, if you're looking at hundreds of thousands of messages a second, Kafka's probably a good thing to automatically reach for. It scales horizontally, supports pub, sub, and point-to-point, and allow the no-cost addition of consumers. So the more consumers I have in ActiveMQ, the system slows down because it has to actually add them into a round-robin dispatch mechanism. Kafka, on the other hand, you can just keep throwing consumers at it. Kafka will just keep performing at the same rate. And also to permit replays. Queues don't allow you to perform replays. Kafka does. It's a fundamentally different model. In order to do this, it uses a unified destination model, where they introduce something called a topic, which I've called a K topic here, just to disambiguate it from a topic. It is both the same thing as a topic and a queue. To implement this, you have one journal per topic with multiple pointers pointing to internal locations. What exactly are these pointers? Well, a pointer is kind of my way of talking about it. You could call it a cursor as well. It's not the actual real name. In Kafka, these things are documented as what's called a consumer group. In code, they're referred to by a group ID. This thing corresponds to a single logical consumer, or a system. Okay? How exactly does this work? Well, with a topic, we've got a journal with some messages inside it. Okay? We have a consumer that connects. It has a pointer called sys_a, because that is the name of the system. And that pointer moves in order to feed it messages. Okay? So the Kafka topic behaves like a queue, where you only have one consumer. However, it also acts as a topic if you've got two consumer groups. key thing is these are two different systems. They're not the same system. They're not two instances of the same system. Okay? If I have one consumer for this holding one pointer, then all the messages come across to it. If, however, I set up two consumers, the second consumer will take all of the messages. This is completely different from the way that ActiveMQ works. ActiveMQ would just start giving you messages in a round-robin fashion. Right? But with Kafka, the second consumer basically takes exclusive consumption of the entire topic for that consumer group. So it's a bit like a consumer priority feature in JMS, but the newest consumer always has the highest priority. Okay? So how do you get about this if you wanted to handle this in multiple threads? Well, you might have one consumer. This is the way that the Kafka documentation talks about it. You might have one consumer instance and you hand this out to multiple threads. Well, this is okay, but only certain use cases allow for it. Yeah? The crash of a consumer instance, this entire box, will mean that anything that's in flight is gone. Pfft. Problematic. So there is another option that's built into Kafka, and it's called partitioning. And the idea is that you now take a single topic and you split it over multiple journals. Okay? So these journals are referred to as partitions. You can also think of them as shards, if you're more comfortable thinking in that terminology. So if you have now two consumers, there we go. If you have two consumers, both consuming connected into Kafka, one gets assigned one partition and one gets assigned another partition. They're in the same consumer group. So consumer 1 gets fed the messages from partition 1 and consumer 2 gets them from partition 2. What if we've got less consumers than we have partitions? That consumer will receive the messages from both partitions. Okay? With me so far? Okay, I know this is heavy stuff for an afternoon, so bear with me. So how exactly do messages end up in these partitions? Okay? In ActiveMQ, if you want partitioning, you actually have to build this at the application level. Okay? You sit over two what are called connection factories and you say, okay, this message, that connection factory. This message gets sent over that connection factory. Okay? It's quite an application level thing. In Kafka, it's built in, sort of. So partitioning is performed by the producer. It's not something that gets provided from the broker infrastructure. Okay? But firstly, before we talk about partitioning, let's consider what it is that we're sending. In JMS, we have this construct of a message, which is an object with some headers that contain some metadata and a payload. In Kafka, a message is a key and a value. Okay? The key here is a business-specific grouping used for partitioning. Okay? It corresponds to a set of messages that should be processed in order together. Okay? So this might correspond to maybe an account number or a geographical location or something similar. Okay? The value itself is a payload. So if we want to work out which partition to send this thing into, we need a function. Okay? And that function says, well, given a message, this key value pair, and the cluster state around a particular topic, okay, because a topic at runtime could correspond to any number of partitions. What's more interesting is that you can add and remove partitions at runtime from a topic, which is kind of interesting. So you constantly need to keep track of what's going on inside the Kafka cluster and what the topic itself looks like. So given the state of the cluster and the message, give me a partition number. Okay? So in Java, this is performed through a partitioner interface, which basically takes, there's the topic, there's the key, there's the value, and there's the current cluster state. So the default implementation uses a hash function, which is interesting, because hash functions give you uneven distributions, yeah? Especially when you have a small number of things to partition, or a small number of partitions. Okay? It's also quite interesting because you get in-order consumption problems. So if I have messages A going to that partition, messages B going to that partition, messages C going to that partition, and I all of a sudden add another partition to the cluster, the next message A that comes into it may actually get moved into the third partition and get consumed before the one that was sent to the other. Okay. So we have some considerations when we talk about partitioning. We need to ensure that all related messages end up on the same partition. We need to ensure that there is some sort of evenness of distribution. Otherwise, some of our consumers are going to be doing a lot more work than others. Okay? And we need to consider the stickiness of a key to a partition. So if I'm sending messages A into partition 1, and a hash function would result in it moving to partition 3, well, maybe I'd like to continue sending it to partition 1. Yeah? So there's a lot of stuff that we might need to think about. If we've got this kind of shared state, well, we also have to worry about managing that state across producers. But why do we actually need to do all this? Well, it's to support a fair distribution of messages to multiple consumers without incurring the cost of dispatch. Yeah? So Kafka rephrases the distribution dispatch problem, that's the cost of sending it out to multiple consumers, into one of partitioning. And it gives the responsibility of partitioning over to you. So it can be really, really fast because it's just a pipe. Sort of. So what other complexity is there in sending a message? We've got to now worry about partitioning, right? Okay, well, when we send a message, send, what does it return to us? A future. Well, the future isn't now. Don't send it now. Yeah. What actually happens is inside the Kafka producer library, we have an in-memory queue. So to us, if we happily send and then keep carrying on, and then our node crashes, our producer node crashes, has that actually reached the broker? Maybe. Maybe not. So it could be in this buffer. So are you able to replay if you end up in this situation? Don't know. It's up to you. Well, at least it's fast. So we can tune this back down to make it more reliable by setting this buffer size to 0, calling back on the future, making it synchronous. But that's all we have to worry about, right? It's not, that's the end of it. Not quite. Because on the consumer library, we have a method called poll. Get me a message. Could be message, but there's a letter here, S. So you're getting a certain number of messages. How many messages? I don't know. Could be 1, could be 100. Your consumer crashes. What's happened? So here's us polling. Feed me a whole bunch of messages. The pointer gets incremented. We have no control over when that pointer gets moved. And the node goes, where are our messages? The pointer's already incremented. If we bring up a consumer, has no idea that the failure happened. So consumption here is non-transactional, which means that you need to keep track of the last consumed pointer position. On partition assignment, rewind to that position through something called a seek operation. Or you keep track of the messages that have been processed. On partition assignment, you rewind all the beginning to the beginning of the journal and just replay everything. And then discard anything that's been previously seen. That's called an idempotent consumer. Or you can keep the consumer code simple and only use it when some sort of message loss is acceptable. Yeah? It's completely different use cases. So this is the A10 Thunderbolt. It's the most resilient plane ever built. It's used for close air support. Tanks, vehicles, ground targets. It can deal with anti-aircraft cannon full on. It's designed to fly with 1 engine, half a tail, 1 stabilizer, and half a wing missing. Kafka's just like that. What Kafka does is it actually uses a replication mechanism across every single partition. Okay? It is completely different to the traditional master-slave kind of old-school mechanism of ActiveMQ, which is very similar to what a relational database would do. In Kafka, it's been designed to be cloud-first, to run on simple commodity hardware. It's kind of the NoSQL of messaging. Yeah? Each Kafka topic has a a master, or it's a leader in Kafka terminology, and it has followers, which are kind of slaves, okay, with some sort of replication going on between them. And by keeping track of, so any slave that is currently in sync with the leader, or any follower that's in sync with the leader can take over, which means that Kafka can actually tolerate all but one of the nodes going down. It's basically like flying with half a wing missing. Okay. All of the reads and writes go to the leader. The client is responsible for setting up how many commit responses that they want from this particular cluster before continuing. The interesting thing about Kafka here is that you can have, if we've got 4 nodes, some of these nodes can be leaders or masters for one topic partition, and some can be leaders or masters for another topic partition. Okay, so in this particular case, Kafka node 2 is a slave for one and a master for the other, for another. Okay. The coordination of all of this is actually performed through a distributed registry. So the actual Kafka instances themselves are just responsible for writing backwards and forwards between the disk and handing messages off. So this particular, in this particular case, Zookeeper is responsible for keeping track of which nodes are currently present, which are the topics and partitions that are currently being maintained, who's the leader and follower for each of these partitions, the consumer groups that are currently active in the system, and which journal offsets in the various partitions the consumer groups actually communicate with. Okay? So the implications of this model are fundamentally that there is no need for shared hardware storage. Okay? Which means that it can actually go around not doing syncs, okay? Because it's replicating the writes out to multiple places, which means that you get up to 3 orders of magnitude higher performance in a Kafka than you do on an ActiveMQ. Is it applicable for all use cases? Not quite. As I said, there's no need to sync. So what a positive. The positive trade-offs of this? Well, it's easily scalable. You just chuck more machines at it. Yeah? Increase the number of partitions. It's got a massive throughput due to its resiliency design. And it's easy to run on commodity infrastructure because that's the thing that it was designed to run on. The downsides of it are it's non-transactional. You've got lots of client complexity that needs to be re-implemented across systems and languages. Is every single one of the things in your company that might be using messaging written in Java? No? Okay, well, get ready to rewrite that stuff. It requires an understanding of the internal mechanics and upfront thought to get right, which, by the way, is exactly what I said for ActiveMQ. And it needs lots and lots of disk, because it keeps the messages around for a set period of time. Okay? So how much disk do you actually need? Well, it depends on how far you've set it up to how many messages you've set the system up to retain before you actually start deleting things. So if you want 20,000 messages a second, and you want to tolerate back-end outages of, if you've got 20,000 messages a second and they're 1 kilobyte each, to tolerate back-end outages, you need to have, at a minimum, on each node, 72 gigabytes per hour. That's how much volume is actually getting accumulated on these disks. Okay. So now that you've got a rough idea of these techs, actually, let's talk about what works for you. ActiveMQ, if you've got high individual value messages, that's a good thing. If you care about not missing messages and you want them processed in order, if you're using non-durable publish subscribe, not everything needs to be retained. The disk is cheap, but it's not that cheap. You might use a broker as a transport bridge. So you might have a WebSocket client talking directly into a broker and a C++ client talking AMQP and getting those messages out. ActiveMQ is a good use case. It deals with request reply over messaging, does some simple message routing, and it allows you to span geographical locations. On the other hand, Kafka You'd use it when you've got messaging that's valuable in aggregate. So single messages, lots of messages where in total they mean something. So user activities, log aggregation, UI performance, etc. Yeah. For this sort of stuff, some message loss is acceptable. You've got a huge throughput of data. How huge? Hundreds of thousands, millions of things a second. Or if you're building systems based on event sourcing, where the total state of a system is based on a number of events, because you can always, if a node comes back up, you can just use the queue almost as a database to replay its own state, okay, and get the current working model. Okay. In summary, horses don't fly, usually. Neither gives you all of transactionality, consumer failure awareness, effortless scalability, storage transparency. You need to know what's going on with your disk. Kafka can be affected by disks, believe it or not. Yeah, there's no magic here. And you don't drop and go either of these things in production. That's not the way they work. So having said that, I'd like to propose that we've reached an era of polyglot messaging. NoSQL didn't replace relational databases. It simply filled niches in the use cases that we were addressing. In the same way, Kafka offers an alternative complementary model to regular messaging. And regardless of the system that you choose to use in the end, invest in the time in actually understanding your tools. They're a foundation for the rest of what you're going to be building. And use the right tool where it makes sense. Remember, more logos, less mythos. My name's Jakub Korab. Thank you very much.